Hello! In this lecture we will have a look at probability. Up to now we have looked at in how many ways events can happen. Yet, for instance, to keep your wallet happy or your server running, you also need to know how likely it is that events happen. As always, pause the video if needed. As we now have some considerable skill in counting, we can put it to good use to start counting the probabilities that events happen. Later we will see how the various types of events can be used to solve problems. Let's begin with counting outcomes. Rolling a die has 6 possible outcomes: 1, 2, 3, 4, 5 and a 6. Consequently, the chance to get a 6 is 1/6. What is the chance we get an odd number? Well, there are 3 different ways we can get an odd number: 1, 3 and 5. This means that the chance we get an odd number is 3/6, or half. In general, we can say that the probability that an event occurs is the number of ways an event can happen divided by the total number of possible events. And this is a simple formula for that. P, which is the symbol or the letter we use to give the probability. So the probability of an event is the number of ways event can happen divided by the number of possible events. The probability that any possible event happens is always 1. Imagine you need to hire a bunch of people for your team. 10 candidates are left and they are all equally qualified. To be fair, you decide to toss a coin for every candidate, and if it is heads, you hire the candidate. Now, what is the probability that you hire nobody? Think about it. You need to be able to calculate the probability, P event, so you will need to first obtain the values on the right side of the equation: the number of ways the event is possible and the total number of possible events. Let's start with the latter. Initially, the team consists only of you. After tossing the coin for the first candidate, the number of possible team configuration doubles. Either you remain alone, or the candidate is added. The same thing happens again when you toss the coin for the second candidate. The total amount of team configurations doubles again. It follows that the total possible number of team configurations is 2 to the power of 10. Now, for the number of ways the desired event can happen, this can only happen if you toss tails 10 times in a row. That is one outcome of all the possible outcomes. So P event is 1 divided by 2 to the power of 10. Very small indeed. If the outcome of multiple events do not influence each other, we say that they are independent events. For instance, if you roll a die and toss a coin, then the outcome of the die roll does not influence the outcome of the coin toss, and vice versa. For every die roll outcome, there are 2 coin toss outcomes. If you first throw the die and then toss the coin, what is the probability to throw a 4 and get heads? The total number of possible events is the number of possible outcomes from the die roll multiplied with the total number of outcomes from the coin toss. So that would be 6 times 2 is 12. The number of ways the event can happen is 1. Throw a 4 and toss heads. The probability for the event is 1 divided by 12, which can be written as 1/6 times a half, and that is exactly the probability to throw a 4 times the probability to toss heads. If events are independent, then the probability for a combined event is calculated by multiplying the individual probabilities for the events. Here is a practical example of how this can solve a problem. You have some data that you need to back up safely for at least a year. You can buy a disk that has a failure probability per year of 1 in a billion, 1 divided by 10 to the power of 9. Or you can buy a disk that has a failure probability of 1 in 2000, but that disk only costs 20% of the first one. If you buy 3 of the cheaper disks, the total cost is 60% of the cost if you would buy the highly rated but expensive disk. The probability that you would lose your data using the 3 cheap disks, note those are independent events, is 1 divided by 2000 times 1 divided by 2000 times 1 divided by 2000, and that is 1 divided by 8 times 10 to the 9th. So the option of buying 3 cheap disks is not only cheaper, it is also 8 times safer. Some events cannot happen together, like throwing a 2 and throwing an odd number. They are called mutually exclusive events. If you consider the probability of either throwing a 2 or an odd number, the number of ways that can happen is 1 plus 3. The probability to throw a 2 or an odd number is 1 plus 3 divided by 6, and that is 1/6 plus 3/6 is 4/6. The probability for any of a number of mutually exclusive events is the sum of their individual probabilities. So the probability to throw a 2 or an odd number is the probability to throw a 2 plus the probability to throw an odd number. And that one is 4/6. If 2 mutually exclusive events together make up the total number of possible events, we call those events complementary events. The sum of the probabilities of complementary events is always 1. Consider the following events. A. The outcome of a die roll is a multiple of 3. And B. The outcome of a die roll is indivisible by 3. The only outcomes that satisfy A are 3 and 6. The probability for A is 2/6. A and B are complementary events. By knowing the probability for A, we also automatically know the probability for B. Because the probability for A plus the probability for B must be 1, and that means that the probability for B is 1 minus the probability for A, and that is 4/6. Okay, let's apply this to a simple example that can be quite confusing. John is an avid angler. He wants to increase his chances of coming home with a fish, so he uses 4 fishing rods at the same time. From experience, he knows that in this lake, he has a 25% chance of catching a fish per rod. His logic is that with 4 rods, he has a 100% chance of getting a fish. Sounds logical, right? Well, we know better now, don't we? Because we know how to count. John's error is that he added the chances per rod. He does not understand that you cannot add the probabilities of independent events. And that skews his view of the situation, as is often the case with gamblers. What can we say about his chances? Well, the probability that he catches nothing on the rod is 75%, because catching nothing on the rod is complementary to catching a fish. The probability he catches nothing on 4 rods is 3/4 to the power of 4, is 0.31640,625. Because probabilities for independent events must be multiplied. catching at least one fish on any rod is complementary to catching no fish at all on all the rods. So the probability to catch at least one fish is 1 minus 0.3164, etc., which is 0.6835, etc. As you can see, it's all about the ability to count. In the right way, that is. So, that's it for this lecture. And it was also the last lecture in the course before the code the basics. We now know how to represent ideas and how to count. In the next course of the Before the Code series, we are going to put that to good use when we start with investigating the time and space complexity of algorithms. Well, I hope that you enjoyed this lecture and indeed the course. For now, bye-bye and see you in the next course. Before the Code, No BS CS.